Are we good?
Yeah, it's great.
Okay.
It's great.
Cool. Well, my name's Hannah, and I'm a data science master's student here, so I'm super qualified to be talking about number theory. The very first slide, I think this joke is really funny. If you do not know, this is Wilson's theorem, and it's Castaway, so that's what makes it funny. Cool. Well, let's go to the next slide. Is that?
Not the button? Yeah. I still have to go through it.
Okay.
My fault. Once. No.
And now the camera is also off. Whatever button we press for that, we press it. Okay. The very first thing when we're dealing with number theory is we have to define divides, right? We have notation A divides B. And all this means is that B is equal to AK for some K and Z, for some integer K. For instance, like 8 is equal to 2 times 4. 4 is our integer K. Okay. So once we define that, we can go to the next slide there. I can press it too. Sweet. So we're going to use this definition just to confirm a few things. First, we're going to confirm that 1 divides A. This is very clear because A is equal to 1 times A, and A is an integer. Okay. And then we have -1 divides A. So we have A is equal to -1 times A. This is probably just going to be a negative integer. Well, not negative. This is just A. It works, okay? So then we have A divides A. This is very obvious. We have A is equal to A times 1. Yeah. Okay. And then last thing we should check, -A divides A. So we have A is equal to -A times -1. Yep. Russell's have 1. You need a negative there. Yeah. Okay, cool. So all those things worked. So we can continue along our journey of number theory here. Yeah, okay. So now we're getting to be able to rack up these QEDs. The very first thing we're going to do is prove that if C is not 0 and AC divides BC, then A divides B. So if AC divides BC, should probably write with the right part of the marker, we know that BC is equal to AC times M for some integer M in Z. As C is not equal to 0, we can divide, I'm not going to write this, BC is equal to AC times M, C is not 0, we can divide both sides by C to see that B is equal to AM, which by definition says that A divides B. Okay? QED. All right. Don't hate the player, hate the game. This is my section. Okay. So we'll go to the next one there. We're at the next one. So we have, if A divides B and A divides C, then A divides B plus C. So we have A divides B and A divides C. Thus, C is equal to AM and B is equal to AN for some M and N and Z. Thus, B plus C is equal to AN plus AM, which is equal to A times N plus M. And as this is an integer, we see that A divides B plus C. QED. We should have put like a wager on this.
I know where would you drop the bar to? Maybe go there.
Okay, next one, another lob of a proof. If 6 divides n, then 3 divides n. Okay, as 6 divides n, we know n is equal to 6k for some integer, or I guess some k in z, right? Observe n is equal to 6k, which means that n is equal to 3 times 2k, which means that this is equal to 3 times some integer, which implies that 3 also divides n. QED. All right. Try to formulate and prove a more general version. Maybe this one doesn't count if we have a more general version. Anyway, the kind of more general version of this, the previous theorem, was if A divides B and B divides C. Does anyone see it? A divides C. I gave you a hint. Does anyone see it? Anyway. So we can prove this. Given that A divides B and B divides C, we know that B is equal to AK and C is equal to BK prime for some K prime in Z. So we can observe. I like using observe in these kind of observe. C is equal to BK prime, right? And B is equal to AK, so we can make a substitution here. So you have AK times K, and this is just an integer, so we have A times K prime. This is also an integer, so we see that A divides C, QED. Okay. There's a bunch of short ones, and then they'll get longer. Okay. So if we have, now we have another theorem. If A divides n, then A divides m times n. So if we're given that A divides n, we know that n is equal to AK for some k in Z, right? We can just multiply both of these sides by m, AK, and do some switching around. This is an integer. Thus, A divides m times n. QED. All right, this one's actually kind of fun. Prove that the sum of 3 consecutive integers is always divisible by 3. We're just going to take the 3 consecutive integers n minus 1, n, and n plus 1, and observe that n minus 1 plus n plus 1 is 3n. So this whole thing is equal to 3 times some integer. Thus, 3 divides this whole thing. QED. Okay. Yes, all right. One last short one here. I did already prove this. Let's go back. A lot of these are just very similar. I think I did prove this. Yeah. No, I think this is the third thing that I proved. Yeah. But yeah, instead of B and C, I have M and N, so I don't think that counts as a separate QED. Okay. All right, so let's go to the next slide here. Basically, to kind of speed this process up as we get into like, yeah, we need speed so we can get these QEDs. Okay, to speed this process up, I'm going to introduce kind of just a new way of like just a new equation format. So the difference, a minus b equal to nk, where k is an integer, can be written as a is congruent to b mod n. And this is like modulo. Okay, so that's all this notation is. It's just a fancy way of saying this. And if we go to the next slide there, I'm not gonna, I guess it's the next two slides, so many apologies. I'm not really gonna prove any of these things. Maybe make it big, yeah. Yeah, maybe the previous one. Sorry, I could do this too. Yeah, there we go. These are just like ways that this works. Basically, like the first 5 proofs that I did are very, very similar. Like if you wanted to go and prove these things, all you have to do is just kind of like put it in division form and kind of do some version of the first few proofs that I did. If we go to the next slide, like 6 is one here that's like maybe not the most intuitive, but also I'm not going to prove it. So take my word for it that 6 is true here. Okay. All right, now we're going to get into some real fun stuff here. We're going to lay the foundation first, so don't get too excited yet. But we're going to lay the foundation, and then we're going to talk about the divisibility rules. We're going to do 2 through 13. So get ready. So this is a theorem that we need to kind of speed up the process of these divisibility rules. This can be very quickly proved, but I think it's better if I just use an example here to explain what this is doing. So if I have some sort of polynomial p of x equal to 4x squared plus 5x plus 6, it is totally math legal to say that if like 11 is congruent to 6 mod 5, we can say that p of 11 is congruent to 6 mod 5, or sorry, p of 6 mod 5. And just to kind of illustrate this, we can plug in p of 11 here. So here we're going to take n to be 5, a to be 11, and b to be 6, obviously. So p of 11 is 4 times 11 squared plus 5 times 11 plus 6. And I plugged this into a calculator, and I got 545. Hopefully that's still okay. And p of 6 here is 180. And you will find that 545 is congruent to 180 mod 5. Okay, if you like subtract these, it's 365. And we haven't proved it yet, but our divisibility rules tell us this is divisible by 5. Okay, and this is very obviously 11 minus 6 is 5, so it's definitely mod 5. Okay.
And does this imply bullet point 6 on the previous slide? That was
Bullet point 6?
raised both sides from the same column.
I think you used that to prove this theorem.
Oh, really? Okay.
Yeah. Yeah. But anyway, questions about that? Okay. Cool. Okay.
Don't worry.
Okay. So I'm not really like technically defining base 10 integers, but we should just kind of talk about what they are. So if x is a positive integer, we can write x as am minus 1 dot 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 a4 a3 a2 a1 a naught, where each a sub I is a digit of x. Okay, so like am, I guess I could just use this here. Like this is the ones place of x. This is the tens place. And this is the 100s place. This marker is slowly dying. New marker. Okay. So we can write x to be, oh, that's a much better marker. A naught plus A1 times 10 plus A2 times 100 plus dot 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 plus AM times 10 to the m. Okay. Cool. Erase. And now we can get to the divisibility rules. I think one's pretty, I'm not going to cover one. We're going to start with two. Okay, so we have an integer is divisible by 2 if its last digit is even. Okay, so we know we're going to get quite a few QUDs from this. We know 10 is congruent to 0 mod 2. Yeah, as 2 divides 10. Thus, by 6, 10 to the k is congruent to 0 to the k mod 2. For, I think it's just k greater than or equal to 1. So we can essentially do this. We can also multiply by both sides of these. That's kind of just in that previous theorem. So since we know 10 is congruent to 0 mod 2, we can multiply both sides by a1, and it's okay. We can do the same thing for a2 and 10 squared, because we have this piece and 0 squared. All the way until am 10 to the m is am 0 mod 2. Okay, and we can just add up all of these things and add up all of and add up all of these things to get a1 10 plus a2 10 squared plus dot 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 plus am 10 to the m is congruent to a1 times 0 plus a2 times 0 plus dot 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 plus am times 0 mod 2. This is 0, yeah. We have 0 mod 2. Okay. And what is this missing? If this is going to be, if this is our base 10 number x, we have a0 plus a1 times 10 plus dot 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 plus am 10m. If we want to say something about x, what should we do to both sides of this if we start at a1? Yeah, we add a0 to both sides. So this plus a0 plus a0. So we just get x is congruent to a0 mod 2. But what is a0? It's just the ones place, right? So we see that, terrible board work, but we have that if x is congruent to 0 mod 2. This is true if and only if A naught, yeah, A0 is congruent to 0 mod 2. QED. Questions about that? Okay. And then we could go to the, oh yeah, Michael, you're on it. Okay. Leave that up. So now we're going to do our divisibility rule for 3. Basically, an integer is divisible by 3 if the sum of its digits is divisible by 3. I should have known that from the top of my head, but whatever. Consider that 10 is congruent to 1 mod 3. Yep. Okay. Thus, P of 10 is congruent to P of 1 mod 3. Note that P of 10 is just A naught plus A1 times 10 plus dot 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 plus AM times 10M, and P1 is just equal to A naught plus A1 times 1 plus dot 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 plus AM times 1 to the M power. This is just a base 10 number. We'll call it N. What is this? Yeah, this is just the sum of the digits of this base 10 number. We'll call this S. So by that previous theorem that we proved, since these are just polynomials, this is true. So we're calling this N, and this is S. So we could just sub them in. So N is congruent to S mod 3. So N is congruent to 0 mod 3 if and only if S is congruent to 0 mod 3. QED. All right. I will say 4 gets a little more interesting. 3 and 9 are pretty similar. Four. Okay. So a number is divisible by 4 if its last 2 digits are divisible by 4. So we know that 100 is congruent to 0 mod 4. Great. Thus, 10 to the k is congruent to 0 mod 4, where k is equal to 2, 3, dot, dot, dot. Thus, a squared times 10 squared plus a3 times 10 dot, dot, dot plus am times 10 to the m is congruent to a2 times 0 plus a3 times 0 plus dot, dot, dot plus am times 0 mod 4. So I'm just combining a couple of rules that we've already talked about. Like we can add things and raise things to powers and we're okay. So this is just 0 mod 4. And note that if we want this to be a base 10 number, I think we're calling it, we'll just call it x, we're just missing 2 pieces, right? Like if we add a0 plus a1 times 10 to this, we'll get a base 10 number. So what we're going to do is just add this to both sides to get x is congruent to a0 plus a1 10 mod 4. So this is just it. Basically, x is congruent to 0 mod 4 if and only if the last two digits of x are congruent to 0 mod 4. So a0 plus a1 times 10 mod 4. Oh, I forgot the 0 piece. Congruent to 0 mod 4. QED. All right. Then we'll go to 5. Okay, an integer is divisible by 5 if its last digit is 0 or 5. I already kind of used this, so we were good when we used it before because we're proving it now. But we know 10 is congruent to 0 mod 5. Cool. Thus, 10 to the k is congruent to 0 to the k, which is congruent to 0 mod 5. Just for k equal 1. So then we get a1 times 10 to the 1 plus a2 times 10 squared plus am 10 to the m is congruent to a1 times 0 plus a to the plus dot 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 plus a to the m 0 to the m mod 5. This is just 0. We get mod 5. And then what do we need to make this into a base 10 number? Yeah, we need a0. So what we're going to do is add a0 to both sides. We're going to call the number this makes x. So x is congruent to its first digit, mod 5. So x is congruent to 0 mod 5 if and only if x is congruent, a naught, a0 is congruent to 0 mod 5. QED. We're getting close. I think I just need 5 more. Okay, this is like the only, I basically have already proved 6. Like that's not gonna count. That's not gonna count. And honestly, if we feel comfortable, we can skip 6. Because I think I already did. I guess I did. I proved it for 2. Well, no, that we already have. Like, let's be fair about this. I've already proved it, so it doesn't. We can't double count, especially not in here. Yeah. Okay, we'll skip 6, but we're on to 7. Okay, 7 is where things get a little dicey. So let's just start with our number. Let's let n equal a to the n, 10 to the n. Sorry for the change. This is the same as m. I did these notes at different times. So a to the n minus 1 times 10 to the n minus 1 plus dot, 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 plus a1, 10 plus a0. Okay. This is equal to, we're going to pull a 10 out, but not from everything. an 10 to the n minus 1 plus an minus 1 times 10 to the n minus 2 plus dot, 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 dot. 4 dots there, so dot, 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 plus a1 plus a0. And then we're going to add a fancy 0. So I don't want that line. We're just going to plus 0, where this 0 is going to be plus 20 a0 minus 20 a0. So this is now equal to 10 times an. I really should have called this something, but whatever. 10 to the n minus 2 plus a1. I'll just write it again. 0 minus 20a 0. Okay, so we have this. What we're going to do is take this negative 20a 0 and put it into here. So we'll have all of this. We'll do like 10 to the an plus a1 minus 2a0 plus a, we're going to just simplify to 21a. Are we okay with that? Okay, cool. So in order for n, I guess in order for 7 to divide n, 7 needs to divide this piece, and 7 needs to divide this piece. We're okay here, right? 7 divides 21. So we need, like, the whole, like, divisibility rule depends on this piece of our equation. And more so, like, obviously 7 does not divide 10, so we're just going to be looking at this piece. So basically, n will divide, or 7 divides n if this piece is divisible by 7. So we have n is congruent to 0 mod 7, if and only if an 10 to the n minus 1 plus dot 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 plus a1 minus 2a0 is congruent to 0 mod 7. And if you note that this is exactly what the theorem statement says, maybe make it big so people can read it again. An integer is divisible by 7 if twice times its last digit subtracted from the value of the remaining digits, so this is the remaining digits, is divisible by 7. So this is exactly what the theorem statement is saying. It just looks a little funky. Questions about that?
You can like repeatedly use this.
Oh yeah, you can get it like down to something that's like really manageable. Yeah. Cool. QED. All right. 8. I think 7 and 13 are the coolest ones. 11's no, I think 11 tops both of them. Yeah. I was gonna do like 51, but yeah, it's kind of crazy. Okay, so an integer is divisible by 8 if its last 3 digits are divisible by 8. We've seen all of the tricks here before. 10 to the n plus dot 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 plus a1 10 plus a naught. Consider. That's a good proof language there. 10 is congruent to 2 mod 8. Okay, so then we could just do our rule where we can raise both of these sides to a power. So we know 10 squared is congruent to 2 squared, which is congruent to 4 mod 8. We can do it again just to make sure the pattern, it'll always, actually no, once we get 10 to the 3, we get 0 mod 8, because 2 cubed is 8. Does everyone see that? Okay, cool. So 10 to the k is congruent to 0 mod 8 for k greater than or equal to 3. So basically we get n is congruent to 0 plus, plus a2 10 squared plus a1 10 plus a naught mod 8. This is essentially the same thing as like 2 and 4, and now we're at 8. Funny how that all worked. So these are just the last 3 digits of n. We'll call them s. So n is congruent to 0 mod 8 if and only if s is congruent to 0 mod 8. QED. Cool. All right, 9 and 3, again, are very similar. Okay. So yeah, an integer is divisible by 9 if the sum of its digits is divisible by 9. We know that 10 is congruent to 1 mod 9. So P of 10 is congruent to P of 1 mod 9. This is going to just be a base 10 number. We're going to call it n. If you recall from the 3, this is just going to be a0 plus a1 times 1 plus am times 1 to the m, where this is just the sum of the digits of n. So we see that if we call this n and this s, n is congruent to s mod 9, and n is congruent to 0 mod 9. If and only if s is congruent to 0 mod 9. Okay. QED. We're really close. I think I do have 10 on there. 10 and 5 are very similar. But we're going to do all the divisibility rules, and then we can skip stuff. Yeah, we're doing pretty good time. Okay. An integer is divisible by 10 if it ends in a 0. We know 10 is congruent to 0 mod 10. Yeah. Okay. So P of 10 is congruent to P of 0. This is just a base 10 number, n. This is just going to be, like, I could write it out, a0 plus a1, 0 plus dot 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 plus am times 0 to the m. So it's literally just the first, it's just the ones digit of n. So we see that n is congruent to a 0 mod 10. Okay, so n is congruent to 0 mod 10 if and only if a 0 is congruent to 0 mod 10. QED. Okay. All right, now this one's cool. Okay, 11. Very cool. There, you can do this one in a couple of different ways. I just picked, I think, the coolest way to do it. So we know, all of these start with a we know, that 1 is congruent to 1 mod 11. Yeah. And so then 10 is congruent to 10, which is congruent to negative, I don't know why I have 10 there. Yeah, it's congruent to negative 1 mod 11. And so we can start like squaring both sides. So 10 squared is congruent to 1 mod 11. And then 10 cubed is congruent to negative 1 mod 11. Dot, 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 dot. And so we see that for our formula, P of x, which is the sum of k equals 0 to m of am, just as a reminder, that was a while ago, x to the k, P of minus 1 is going to equal the sum k equals 0 to m of ak minus 1 to the k. So P of 10 is congruent to P of minus 1 mod 11. This is just a base 10 number. This part is cool. So this is just going to be a0 minus a1 plus a2 minus a3. You see where it's going? Plus dot, 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 plus minus 1 to the m, a to the m. So this is just like taking the digits of this number. And so you start with the ones digit, you subtract the tens, add the hundreds, so on and so forth. And so if this number is divisible by 11, then the original number is divisible by 11. So we'll call this t. N is congruent to t mod 11. So 11 divides n if and only if 11 divides t. QED. I just need one more, and we have it.
T is the result of doing that alternating trick.
That's just what I called it, yeah.
No, that's. Could it? Oh, but T could be really large or small.
Yeah.
Maybe have a long number.
There's also, like, you can also do the 11 divisibility rule if you, like, there's a fancy add 0 trick, like we did for 7 or 11. But I think this one was just cooler. All right. Yeah, 13 is going to use that add 0 trick. Good intuition. I'm skipping 12. We're going to 13. Yeah. Okay, an integer is divisible by 13 if after adding 4 times its last digit to the number formed by removing the last digit, the result is divisible by 13. It's pretty intuitive. Okay, so we have n, which is just like 10 to the m, a2 plus am plus, we know the drill at this point, right? I switched these for some reason. That's just where the notation took me. So we have am plus, oh no, yeah, 10 times a1 plus a0. We're going to do the fancy pull out and 10 trick. We have 10 to the m minus 1 times am plus 10 to the m minus 2 times am minus 1 dot 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 plus a1 plus a0. Does anyone want to guess what the fancy add 0 is going to be? Well, 4 is... Yeah, it's 40. So we're going to subtract and add 40a0 to this. Okay. So I'll just do that. And then we're going to take this guy and put it in our parentheses. So we have 10 times 10 to the m minus 1 times am plus 10. I don't need to do that. I think we know what we're doing. Okay. So we have plus a1 minus 4a0 plus I think I wanted to put the plus in there. Sorry. So we're doing minus 39. It doesn't really work if it's not divisible by 13. So, yeah, we're good there. Okay, so this number n, it'll be divisible by 13 if both of these pieces are divisible by 13. Actually, I think it's supposed to be the other way. No, I think we're okay. Okay, so this number is already divisible by 13. 13 times 3 is 39. So we're okay here. And we need this piece to be divisible by 13. There's no chance for 10. We know 13 does not divide 10. So we're really depending on this piece here. But if we note, this is just quite literally the theorem statement. So we take 4 times the ones digit, add it to the rest, the digit formed by the rest of the numbers, and if this number is divisible by 13, then our whole number is divisible by 13. Okay, cool. So I think we're okay to just QED it, right? We feel good? Okay. All right, I'm winning, so.
Would you feel about an example?
An example of this? Well, we got 39. So. Maybe that was a poor example. Maybe we need a bigger number. Does someone want to pull out a calculator and get a... All right. 169. And what does the theorem statement say? So we take 4 times this digit. 4 times 9 is equal to 36. It's been a long day. So 36 plus, looks like, okay, plus 16. What is that going to come out to be? 52? 52? Is that 13 times 4? See, it works, and I knew it worked because we proved it. All right. What's next? All right, we're getting into some primes. Okay, and then I kind of did a little bit of research on number divisibility rules past 13, and they pretty much have that flavor of adding a fancy 0 to them. So, yeah. Okay, primes. So an integer p is prime if it's only divisible by integers 1 and itself, and we call non-primes composite. The first 10 primes are 2, 3, 5, 7, da 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 da. I think we're good to go. Okay, cool. Let's just go to the next slide. We all know what primes are. So we're going to prove that if p is a prime and a and b are integers and p divides a and b, then either p divides a or p divides b. I think the or both there is kind of implied after this, but whatever. Proof. Okay. So if we recall, there's nothing much to recall because I haven't talked about this before. Euclid's lemma tells us if a prime divides b prime c prime with the GCD of a prime b prime equaling 1, then a prime divides b prime. Okay, so we have if p divides a, we are done. Okay, we've already done the theorem statement, so we're good. So we're really only concerned about if p does not divide a. Also, we're just assuming a or b here. Okay, so if p does not divide a, we are not done. Yeah, QED. Okay, but what we do know, if p does not divide a, then the GCD of p and a is 1. So our two pieces work together here to get to our goal. So we know that p divides b times a, and the GCD of p and a is 1. So by our lemma up here, we see that p divides b. Okay, and then as and so technically there, at that point, we have shown that if p divides a times b, it'll divide either p divides b or p divides a, because we showed 1 was true. But you can also do the same argument for 1. But yeah, that was pretty quick, thanks to Euclid. Questions? Okay. Move on. Oh, this one's cool. Okay. So we have proved that every integer n greater than 1 is divisible by some prime p. Okay. If n is prime, we are done. Right? We know this. If n is not prime, we are not done. But if n is not prime, we can let n be the product of two integers x and y, where n, I guess we can just let x equal just not n and y equal not n, right? Otherwise, we'd be in a prime situation. If x or y are prime, we're done. If not, if not, we'll do this again for x. You could also do it for y, right? Let x be the product of two integers that are not x. And just keep going until you hit a prime, right? And eventually, if you do that enough, you'll find a prime that divides n. Okay. QED. Okay. Every composite, okay, so the theorem statement is, prove that every composite integer that's greater than 1 is divisible by some prime p that is less than the square root of n. Okay, so we're just going to suppose n is composite. We're given that. We don't need to suppose it. But we can let n equal x times y because it's composite, where x and y here are integers. Also note that x and y cannot both be larger than the square root of n. Like, this is not possible. Because otherwise, you multiply them together and you get a number that's greater than n, and that just does not work. So this cannot happen. So we're just going to pick one of them. Let's pick x. Let's pick x just to be the one that we know for sure is less than or equal to the square root of n. Like, in doing this, y could be greater than the square root of n, but we know for sure that one of them has to satisfy this, right? Okay, so we're going to suppose that it's x, and by the last theorem that we proved, we know x has a prime divisor. Okay, so x has a prime divisor that will either be, prime itself, so this has a divisor that is less than or equal to x because it's a divisor, right? Okay, so getting off topic, as p divides x, we see that p divides n and is at most the square root of n. QED. Cool. Okay. Yeah, we're doing okay. We'll go to the next one. Actually, let's just skip this one. I think we have better ones. Okay, I'm not proving this. Yeah, but it's true. Okay, so basically we have the fundamental theorem of arithmetic that says for every integer that's greater than 1, the integer has a unique prime factorization. We'll just do a couple of examples of this if we go to the next slide there. We're going to find the prime factorization of 42, 101, and 850. So I prefer the little tree method. I think it's fun. So we could just find two numbers that multiply to be 42. Take 7 and 6 work. And then from here, we're going to break up 6. So we have 3 and 2. So we see that 42 is equal to 7 times 3 times 2, right? And so this is the prime factorization of 42 because these are the primes that factor 42. Okay, so 101. Does anyone know anything, a fun fact about 101 that might? It's prime, yeah. So basically it's just 1 and 101. So it is its own prime factorization. Okay. Is 850 prime? No, we just proved all those divisibility rules. So we know it's divisible by at least 2, 5, and 10. So we do 10 and 85, right? This can be 2 and 5. 85 breaks into 5 and 7. So 17, yep. We've been at it for a while. Okay. All right, so 850 is equal to 2 times 5 squared times 17. Okay, cool. Go to the next one. It's just another example of prime factorizations. Yeah, let's perhaps, we could skip this one. Okay. So this one's kind of cool. Explain why a number with 30 digits cannot have more than 100 prime factors. Basically, if we think about the smallest number with 100 prime factors, does anyone have like intuition for what this would be? Yeah, 2 to the 100, which is just 100 twos. Okay, note, 2 to the 100 is equal to 1 times 2 times 6 times 7 times 6 times 5 times a lot of things times 0 times 5 times 3 times 7 times. Not times. This is just a number, right? Okay. All right, this is a number. Okay, so note that this number has 31 digits. So this is the smallest number with 100 factors. It has 31 digits. So there is no number with there, like we go back to the problem, there is no number with 30 digits and 100 prime factors. So that's fun. Are we good to go? Okay, so we're trying to prove that there are an infinite number of primes. Typically, when you have a proof that says prove that there's an infinite number of something, what do? Suppose there's not an infinite number of that something and contradict it. So what we're going to do is suppose, for the sake of a contradiction, that there is not an infinite number of primes. Okay? As there is a finite number of primes, we can list them. And here they are. We have P1, P2, all the way up to PK. Okay? However, by the previous theorem on this slide, we know that P1, P2, up to PK plus 1 is a prime, right? So we know that P1, P2, ... This is a multiply. PK plus 1 is prime. Is not primes, it's prime. Is it in this list? No, right? It's not in the list. Contradiction. Use the fun arrow there. But it is prime, so it has to be in the list of primes, so it's a contradiction. Okay. QED. Okay. And then we go to the next slide here. Oh yeah, this one's a really good one. It's that there are an infinitely many number of twin primes. It's 444. Unfortunately, I think we have more important theorems to prove. So I'm going to move past this, but I will give a hint for the people at home. If you want to try this, here's a really good hint. And basically, if you do this, it's pretty much trivial. So, yeah, QED. Yeah, we'll count it.
The people at home.
Okay. Cool. I'm gonna drink some water. Okay. This is one of the more important theorems that I was talking about. Actually, it's a lemma. Forgive me. So we have a lemma here. Our goal is to prove that for all natural numbers n to the n minus n is congruent. So I'll just write here, n to the n minus n is congruent to 0 mod 2. Okay? If 2 divides n, we're done. If 2 does not divide n, guess what? We're not done. Okay? I'm going to introduce a theorem here. It's Fermat's little theorem. And basically it tells us if p is prime, then a to the p minus 1 is congruent to 1 mod p. Okay, so we know, because 2 is prime, that n is congruent to 1 mod 2, which implies that n to the n is congruent to 1 to the n, which is congruent to n, n, because we have here, mod 2. So we're done there. And we can go to the next lemma. It's the, lemma 2 there. So here's just the next one. All right, lemma 2 is if n is odd, then n to the n minus n is congruent. So if n odd, n to the n minus n is congruent to 0 mod 4. This is another sort of introduction. It's very, very similar to Fermat's little theorem, but it's a stronger result. This is one of Euler's theorems, is that if n is greater than or equal to 1, and the GCD of a and n is 1, then a to the phi I think it's phi, I don't know, is congruent to 1 mod n. This is the I'm going to use. As n is odd, we know that the GCD of n and 4 is 1. So that's going to be used here. And in terms of using our theorem here, we have a to the phi. We got to sort this out now. Is it phi or phi? Phi. And we'll write it down so I remember, but I'll forget. Okay. So phi, a to the phi of 4. Also, phi is just the number of divisors that are below 4. So for 4, it's a squared. Yes, a squared is congruent to 1 mod 4. We can raise both sides to the power of k. So we see a to the 2k is congruent to 1 mod 4. So a to any even number is congruent to, I think this is supposed to be an n. N. We're not here, we're here. Okay, yeah, much better. So we know that n to any even number is congruent to 1 mod 4. So we can write n to the n minus n as n times n to the n minus 1 minus 1. We know that this is even as n is odd. Okay, so we know by this that n to the n minus 1 is congruent to 1 mod 4. So this piece of this is divisible by 4. Thus, this whole thing is divisible by 4. Okay? Oh, I'm not counting the lemmas. That's where we're at. We're at lemma 2. Okay. Next lemma. Lemma 3. Oh, no, it's cut off. Well, for those of you at home, it's very similar to the first two. It's just there's another. Oh, yeah, nice. Okay, so we have n to the n to the n minus n to the n is congruent to 0 mod 3. Oh, I erased my reminder. Okay. Cool. So we have n to the n to the n minus n to the n is congruent to 0 mod 3, where n is greater than or equal to 2. Maybe I forgot that, but it's important. So we have if 3 divides n, done. If not, you guessed it, we're not done. Okay. Not done.
True for n equals 1?
Let me make sure this is saying the right thing. N to the n. So basically 1 minus, yeah. Yeah. Well, eventually, I think like, yeah, whatever. Doesn't matter. We proved it, so sorry. Okay. All right. So by Euler's theorem, we know that n to the phi of n of 3 is congruent to n squared, which is congruent to 1 mod 3. So this implies, like, we can raise both sides to the power of k. So we have 2k congruent to 1 of the k, which is congruent to 1 mod 3. So n raised to any even power is congruent to 1 mod 3. So we can write n to the n to the n minus n to the n to be n to the n times n to the n to the n minus n minus 1. And for those of you who are paying attention, by lemma 1, n to the n minus n is even. Okay, so we know this is even, so we're going to use this. And we're going to use it to say, that's funny, the congruence with so implies n to the n to the n to the n to the n minus n is congruent to 1 mod 3. So we know this piece is divisible by 3, so this whole thing is divisible by 3. Cool. All right. Yeah, we're on lemma 4. Woohoo. Okay. 4 of 7. So we're almost there. More than half. We're at half, ish. I think maybe not 2. Yeah, 2. Maybe the first one that we questioned was it true for 2? 2 to the 2 to the 2 minus 2 to the 2. Is that divisible by 3?
Yeah.
Is that okay? So I don't know where I got that from, but that was in the past. So we'll go to, if n is greater than or equal to 3, n to the n to the n minus n to the n is congruent to 0 mod 16. N to the n to the n minus n to the n is congruent to 0 mod 16. Okay. So if n is even and greater than or equal to 4, we're done. If not, not done. Okay, so if n is not even, if n is not even, then we know the GCD of 16 and n is 1, which implies that n is odd. Well, if it's not even, it already implies that n is odd. So maybe this is a better direction for that. And then we're going to note that n to the n to the n minus n to the n is equal to n to the n times n to the n to the n minus 1. Okay? And as n is odd, we see that n to the n minus n is congruent to 0 mod 4 by lemma 2. Okay? And I wish I would have left myself more room, but whatever. I'm going to define something here. So we have a Carmichael function. Michael. Michael function, lambda of n. And basically, it is the smallest integer m such that a to the m is congruent to 1 mod n. So it's basically a reduction of Euler's quotient theorem, where before this was phi of n, but this is m, and they're not necessarily going to be the same. This is less than or equal to. Okay, so for example, well, not even example. We'll just leave it. Okay. I think I wish I would have kept that, but whatever. Okay. So the theorem that goes with that is that if the GCD of an is 1, we know that a to the lambda of n is congruent to 1 mod n. And for 16, lambda of 16 is 4. So we see that n to the lambda of 16 is congruent to n to the 4, which is congruent to 1 mod n. We see this. We could raise both sides to the power of k. So we see n to the 4k is congruent to 1 to the k, which is congruent to 1 mod n. Okay?
Can I ask you a question?
Yeah, of 16.
The lambda to the n was the minimum, what, m?
Yeah, it's the smallest integer m such that a to the m is congruent to 1 mod. And yeah.
Okay, so it's written as lambda n, obviously depends on n.
Yeah. Sounds down again.
Really?
Is it me? Is it dying or something?
Been dying fast, but this one has battery.
It's still blue.
New Testament. I'm hearing audio here still.
Oh, okay.
Yeah, you're good.
Are we good? Okay. So, where are we at in this? We have that n to the 4k is congruent to 1 mod 16. So, we see that n to the n to the n minus n is congruent to 1 mod 16. As 4 divides n to the n minus n. So then we see that n to the n to the n minus n to the n is congruent to 0 mod 16. QED. All right, we're ready for lemma 5. Is it up? Oh, we're waiting. Okay. Okay. So, lemma 5 is that if n is greater than or equal to 3, then n to the n to the n minus n to the n is congruent to 0 mod x, where x is equal to 6, 12, or 16. Okay? So by lemmas 3 and 4, we see that n to the n to the n minus n to the n is divisible by both 16 and 3, which gives us that it's divisible by 2 and 3, 2 and 3, and 4 and 3, 4 and 3. So it just falls out that this is true for 6, 12, or 16. Cool. Cutie. Lemma 6. I need a second win with these lemmas. There's a lot of them. Okay. Lemma 6 is perhaps. Does anyone have a guess what lemma 6 might be about? That's a very good guess. Maybe one n off, maybe? I don't know. Okay. So we have if n is greater than or equal to 3, then n to the n to the n to the n minus n to the n to the n is congruent to 0 mod p, where p is 13 or 17. Okay. So if p divides n, done. You guessed it. If p does not divide n, we're not done. We're going to write n to the n to the n to the n. Yes, 3 n's minus n to the n to the n as n to the n to the n times n times n to the n to the n to the n minus n to the n minus 1. Okay. We know that this is divisible by 12 and 16 by lemma 5. We know that lambda of 13, as this is prime, is 12, and lambda of 17 is 16. And because p does not divide n, we know that the GCD of p and n is 1. Thus, n to the lambda of p is congruent to 1 mod p. So, either n to the 12 is congruent to 1 mod 13, or n to the 16 is congruent to 1 mod 17. We can raise this to k and raise this to k and see that n, are we still okay? Yeah, is 12 times k is congruent to 1 mod 13. And we could raise these both to the power of k, so n to the 16 to the times 16 times k is congruent to 1 mod 17. Okay, so note that we know that there's a lot of n's going on. N to the n to the n minus n to the n is a multiple of 12 and 16 by a previous lemma. I don't remember which one, but take my word for it. So we know this is divisible by 12 and 16. We have these two pieces. Thus, this is true because this is now divisible by 13 or 17. Okay? Yeah.
How did you know lambda of 13 and 17? Is that just like computation? Or...
Well, the numbers less than 13 that are not divisible. Let me look at the lambda definition. Is the smallest integer m such that that is true? So, well, like if you think about like for Moz, like this is just quite literally for Moz. So we could just have done that as well and not have to worry about lambda.
Can I also ask about, I fully believe it,
Mm-hmm.
but this factorization of n to the n?
Yeah?
How do you get that exponent?
Oh, here?
Yeah, the big circle part.
Oh, just multiply it through.
Okay, I see.
Okay.
And then that.
So n to the n to the n times n times n.
Surely I'm not the only one.
Yeah, did I mess that up?
No, I
Maybe.
don't think it's wrong.
So we put this back in here. We're going
Wait,
to
what
get,
is
yeah, n to the n to the n to the n, obviously.
that? So the n it's plus n to the n, which cancels with minus n to the n. Okay.
Yeah.
Okay. Yeah. Sure. Yeah. Yeah. Great. Wow.
All right. Guess what? There's only one more lemma. Okay. This one's not that. I take it back. Let's just take a peek at the lemma. Okay. So we have n to the n to the n to the n minus n to the n to the n is congruent to 0 mod 9 for n greater than or equal to 3. Okay. If 3 divides n, that's wrong. Done. If not, we have some more work to do. But if 3 does not divide n, we know that the GCD of 9 and n is going to be 1. So then n to the lambda of 9 is congruent to 1 mod 9. Note that n to the lambda of 9 is n to the 6. So we could fit this in somewhere into the 6. Yeah, okay. So we have that n to the 6 is congruent to 1 mod 9. Multiply both sides, to raise them both to the power of k, so n to the 6k is congruent to 1 mod 9. We know that n to the n to the n minus n to the n is a multiple of 6 from lemma 5. So we could write n to the n to the n to the n minus n to the n to the n as n to the n to the n times n to the n to the n to the n minus n to the n minus 1. We know that this is a multiple of 6 from our lemma. So this whole thing is divisible by 9. So this is divisible by 9. QED. All right, we have made it through the lemmas.
Another question.
Yeah.
If 3 divides n, we're done. Is that from a lemma before?
Well, also, like, you could do, like, yeah, that's a good question. Like, 3k, 3 to the k, 3 to the k, that's 3 to the k, minus 3 to the k, 3 to the k, 3 to the k. I think that's good. You can get 9 pretty quickly.
Okay.
Yeah.
I see.
Yeah. Yeah.
Was that in the previous one? You did something similar. The first step was if something divided it, you were done. Was it the same strategy? Maybe you don't remember.
Well, this is just here. We have to be careful because we're like for where we're going with this foreshadowing. We need this n greater than 3. So and we need 9. All right, let me erase this, and then we'll go to the next slide. When life gives you lemmas, go to the next slide. We prove a theorem. Yay, okay. It's the age-old saying. Okay, so here is what we've been working towards this whole time. Very useful result for everyday life. I'm so glad we didn't prove the twin primes theorem in lieu of this. Okay, so if n is a positive integer with n greater than or equal to 3, then n to the n to the n to the n minus n to the n to the n is divisible by 1989. This, I hope every single one of you this is like your new party trick, that you just know this, and then it's like pull out a calculator. Like, I could show you that this is true.
Actually, can I ask?
Yeah.
Pull out a calculator, but what is the value of this for n equals 3? I don't think you can calculate it. It's already really like.
That's still a fun party trick. All right, we have 1989 is equal to, this reminds, this comes back to Taylor Swift. There's been kind of a theme with the Euler tour this morning. But anyway, 1989 is equal, this is not a hat of any variety, so don't confuse that. Is equal to 3 squared times 13 times 17. Do we see why we've been doing what we've been doing? Okay, so we get that n to the n to the n to the n minus n to the n to the n is congruent to 0 mod 9. This is just from the lemmas that we've been doing. We're going to put this in quotes because I think we all have had enough of these n's. So we have is congruent to 0 mod 13, and it's congruent to 0 mod 17. So we know that if we put all these things together, n to the n to the n minus n to the n to the n is divisible by 1989. QED. I think that's 5, 10, 15, 20, 25, 30. We've more than doubled the previous record. Okay. We did this during the technical difficulties. I think we're skipping to cryptography, which I very much regret with putting that near the end because it's going to be terrible, filled with mistakes now. Just go till you see like cryptography in there. We did that. Did that. Yeah, back one. There we go. Okay. Are we? Okay. Did I spell something wrong or something? Okay. So. Oh, yeah. Okay. Oh, that's good. That was funny. Okay. So cryptography is the science of making communications unintelligible to all except the authorized parties. Defined it. Let's move on. So we're going to be doing we're going to do a couple of different flavors of cryptography here. Very first thing, the very easy sort of problem is the Caesar cipher. I don't know. Anyway, okay. So every time I see this, I'm like chicken Caesar salad, you know, like there's that meme where there's that. Okay. Anyway, so basically, what we're going to do with this Caesar cipher is move each letter. So each letter corresponds to the letter that is 3 letters after it. So here on the sides, I have the plain text and then the ciphertext, which is just the alphabet moved 3 over. Now go back. You're ruining it. No, I'm just kidding. Go back. No, it's good. Okay. So for an example, if I gave you P, D, W, K, D, W, K, R, Q, what does that mean to you? Nothing, right? But if I told you, oh, I used a Caesar cipher, that's so funny. Okay, a Caesar cipher to encrypt this. Now we can go and use this cipher to decode our text. So we'll just do the first few here, like P is S. No, okay, this is the issue. I messed around a really long time just to make it even. It's not even. So don't look at this. It's like slightly off, especially in the middle. But P is M. D is A. You can see that there. W is T. Does anyone, if you can tell where we're going with this, shout it out. D is A. W is T. That's close. K is H. R is O. Mathathon, yeah. So, yay. No one's going to get our secret information. Okay, so now we could go to the next slide. So how is this relevant to number theory? We can use congruence theory to translate the alphabet into numbers to really quickly decode things. So if we let A be like 0, 0, B be 0, 1, da 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 da, so just like numbering the alphabet, we can let P be the digital equivalent, maybe. we're close there with the spelling, of a plain text letter, and C be the digital equivalent of a ciphertext, we'll see that for our Caesar cipher, C is congruent to P plus 3 mod. Anyone know what it's going to be mod here? Yeah, 26. Just because we have 26 things there, right? That's 29. 26. Okay. So this is what we're going to use to encode things. Again, we can use our, just going to check the time. We don't have time for it, but I promise this is okay. There's a lot of issues with using this method. Like, would you want your credit card information encrypted with this? No, because it's very, very simple. I don't even think you need a computer to get that one. So we can move on to a more complicated cryptography situation. It's just on the next slide there. And we can use a polyalphabetic cipher to make things more complicated, so it's harder to decrypt. And basically, it just allows for us to have a plain text letter with more than one ciphertext equivalent. So if we go to the next one, we have this type of cipher, and it's a polyalphabetic cipher. And how it works. Does anyone know how to say that? Like the. Yeah, all right. We'll give it a nickname like Sarah, the Sarah cipher. Sarah. I can't spell Sarah cipher. Whatever. We know what we're talking about. How it works is that the communicating parties are going to agree on a keyword. So we have a keyword. If you do not know, there was a Pi Day lunar eclipse last night to this morning. So I thought it'd be fun to make the keyword lunar and the message eclipse with an E. If you're a bad speller, this is a tough go. Okay, so we're going to find the numerical version of lunar. And this just uses the same like 0, 0 through 25 coding thing that we did before. L is 11, U is 20, N is 13. I wish I would have spaced these letters out more, but whatever. 0. E is 4, R is 17. And for eclipse, I should learn from my mistakes. All right, eclipse. We have 04, 02, 11, 08, 15, 18, and 04. And then we're going to arrange the repetitions of lunar, the numerical sequence of lunar below the numerical plaintext eclipse sequence. So what I mean by that is we're going to take these numbers. So we have 0, 4. Oh no, we're out of room. We've been at this for a while, so these mistakes are okay. We'll put it over here. We don't need the reminder anymore. So we have 0, 4, 0, 2, 11, 08, 15, 18, and 04. 04 goes with 11. So this is just lunar, right? 11, 20, 13, 04, 17. We're out of letters, but does anyone see what we're going to do? Just do it again, right? So we're going to put 11 here, and we're going to put 20 here. And then to encode our secret message, we're going to add these numbers, add the columns, and we're going to make it modulo 26 to encrypt. I'm just going to do this so we don't have to spend time on it because I really want to get to RSA. 24. So we have P W, Y. That's not a Y, that's a 4. 12 is M. 6 is G, D, and Y. So basically, yeah, you send this out to whoever you're trying to have secret communications with. You and them both know the word lunar, right? And so then they can use this word lunar to decode this. And basically, like, the quick way to do it is instead of 3, you're gonna, like, instead of having, like, C is congruent to P plus 3, each of these letters is going to become its own number, mod 26. And that's like kind of the quick version of how that works. Yeah, and we should be almost to RSA. Nice. So RSA, we're going to finish with RSA. RSA is a kind of a beast. So, but you want it to be. Like, this is what's keeping your credit card information safe. Like, anytime you buy something online with the little, like, security, like, lock in the browser, this is what's being used. So, or like those bank key cards that have, like, you know, when you have like a bank keychain and the number is always changing, that's like a RSA key fob. So we're going to prove why it works. So takes a while. Okay. So with RSA, we have 5 variables. We have M is the message, K is our encrypting exponent, N is our modular setting, R is the encrypted message, and J, it's a J, right? Yes, J is our decrypting exponent. So let's go to the next slide there. Oh, just go back. We're on this slide for a while, so get used to it. Okay. So let me skip to RSA. I think just to like kind of give a hint to where we're going, this works because BC, we're going to let N equal PQ, where P and Q are large primes. Okay? And they're going to be so large that it's beyond computational ability to factor this quickly. So it's very, very hard for someone to go and factor this to decode the message. So that is kind of the whole, like, that's like really short version of how RSA works. But we'll also explain everything. Okay, so for example, we're going to let M, this is our message that we're trying to send out, be secret message. I ran out of things that I thought were fun to be messages, but whatever. So M is secret message. We're going to let K be 83. We're going to let N be 4,757. We're going to let J be 167. Okay? So the very first thing we're going to do is we're going to take secret message and space it out properly. Secret space message. Okay, so we have secret message. We're going to just use our numerical versions of these letters like we have been doing. So S is 18, E is 04, C is 02, R is 17, E is 04, T is 19. What do we suppose the space is going to be?
27.
27? We're actually going to make it 26. Because, right, we go 0 to 25. Yeah. 26. M is going to be 08. No, that's an E. E is 04. S is 18. So that means this S is also 18. And then A is 00. G is 06. And E is 04. And then what we're going to do is we're going to chunk these into two. Okay, and I just so happen to pick a message with an even number of things here. But what if this was odd? What would we do here? Yeah, we're just going to add a space bar, but we don't need it. But if it was odd, that's what we would do. Okay, and then we're going to let this be M1. We're going to let this be M2. We're going to let this be M3. And then this one's M4. Any thoughts on what this one's going to be? M5. M6 and M7. Okay. And then we're going to have M1 to the K power be congruent to R1 mod 4,757. Okay. So this is 18,004 raised to the 83, which is congruent to R1 mod 4,757. And now we have to find R1. So let's do that. Okay. The quick way to this is to note that, okay, 83 is equal to 64 times 16 times 2 times 1. So all we need to do is find 18,004 to the 54th power times 18,004. What this would be modulo 4,757. So 1804 squared times 1804. Okay. And so what we can do, one way to do this is you could do 18,004, find all of them and just piece together what you need with the exponents. We're going to skip ahead a little bit. So we have 18,004 to the 83 power is congruent to 18,004. We're going to congruent to this, right? Yeah, we're okay. And this is going to be congruent to 2,225 mod 4,757. And this is R1. Okay? Now we need to find R2 through 7. But I hope that you'll just trust that I plugged this correctly into like Wolfram Alpha, and I will give you all of our R's here. Okay. Any questions so far? Cool. All right. So R1 is 2,225, R2 is 942, R3 is 2,244, R4 is 4,302, R5 is 339, R6 is 2,348, R7 is 2,748, and we have that J is equal to 167. This is something that I said at the start. And so these are the things that you're going to give the receiver. Maybe? They already have this. So if they want to decode your message, they're going to take each one of these, raise it to the 167 power, and they're going to get M1 out. So for instance, if they take R1 to the 167 power, they're going to get M1 mod 4,757, where R1 is 220, 2,255, 167, and this is 1804 mod. 4,757, note that this is the first two letters of our secret message. So we're good there. And it does work for 2 through 7. But something that I think is a lot more interesting is how do we find the message? So we're going to define, so we'll do find. We're going to define relatively prime. Maybe I should have done this before, but better late than never. Relatively prime. So 2 integers are relatively prime if they have no factor other than 1 in common. So if their GCD is 1. Okay. Phi of n is the number of integers relatively prime to n and less than n. Okay, so for example, 5n, 5, 6 is 2 because we have 1 and 5. Phi of 7 is 6 because we have 1, 2, 3, 4, 5, and 6. Okay, so when we choose n to be p times q, where p and q are prime, we see that phi of n is equal to p minus 1 times q minus 1. And so in the case of our example, we have 4,757 is equal to 67 times 71. So phi of 4,757 is 67 minus 1 times 71 minus 1, which is 4,620. Okay, and then I'm going to erase this. All right. Okay, so this is where we get n. So where do we get k from? So this is about k. So we choose k such that 1 is, it's greater than 1 and less than phi of n, and the GCD of k and phi of n parentheses is 1. So in our example, our GCD of 83 and 4,620, right, 5n, is in fact 1. Okay. And, shocker, 83 is greater than 1 and less than 4,620. So, okay, so this is how we get k, that's how we get n. Now let's talk a bit about j. Where do we get j from? We're going to pick j such that it's greater than 1 and less than 5n, such that k times j is congruent to 1 mod phi of n. Okay, so we know k, we got k from our example, is 83. We're going to multiply it by j, and we want to pick this j such that 83 times j is congruent to 1 mod 4,260. So how do we do this? It comes back to Euclid. He's really doing a lot for number theory. Okay. Actually, this is pretty cool. So the cool thing about RSA is it just uses a lot of number theory topics. Like, I didn't cover this, but we're going to see it here. So basically, this is Euclid's algorithm. Algorithm. Okay, and it's going to allow us to find J here. So, and this is just a way to get, I think it's like x plus y equal to 1 or something. I think that's true. I think we're quite a few hours into this. So. Okay, so we have 4,260 is equal to 55 times 83 plus 55. And then we take this 83, and we say that's is equal to 1 times 55 plus 28. We take this 55. So that's 1 times 28 plus 27. And then we take this 28, and this is equal to 1 times 27 plus 1. Okay, so this is how we find the GCD of two numbers. If you do this all out and you can't go any further, this last number is the GCD of the two numbers. So this is what this is telling us. Okay, so we have the GCD of 83 and 4,260 is equal to 1. Okay, and so we're going to use the results of our algorithm. This algorithm over here. I'm going to use the results of the algorithm to find x and y such that the GCD of 83 and 4,260 is equal to 83 times x plus 4,260 times y. And basically how we do this is we just go backwards. So we have 28 minus, oh, this marker is not doing very well. Okay. So we have 28. So we have 28 minus 27. What do we think that is? Yeah, just 1. Got to get the audience involved. So we have 28 minus 27 is equal to 1. But right, we have a formula for 27. 27 is just 55 minus 28, right? If we just take this over here. So we're going to plug that in over here. We have 55 minus 28 is equal to 1. From this, we see that 2 times 28 minus 55 is 1. Okay. And then we have a formula for 28 as well. We see it here. We know this is equal to 83 minus 55. So we plug it in here. We have 83 minus 55. And we get 2 times 83 plus 55 times negative 3 is equal to 1. And then we're going to take it up here and say that 2 times 83 plus negative 3 times, we have an equation for 55. It's just right here. So we have 4,260 minus 55 times 83 is 55. And we're going to plug it in right here. So 4,260 minus 55 times 83. There we go. This is equal to 1. So we can simplify and get 83 times 167 minus 4,620 times 3 is equal to 1. All right, we did it. Does anyone recognize this number? Is it? I heard J. It's J. So this is how we find J. You could also use a computer, but I think there's value in doing it by hand. So this is how you find J. All right, now, so that's how we find N, K, and J. But why does this all work? After I erase the board, I will tell you. Okay. why it works. Okay. So we have r to the j is congruent to m mod n, right? This is how we decode things. But why does this decode our message? Okay, so recall how we got to r. Recall how we get to r. We have m to the k is congruent to r mod n. So this implies that r is congruent to m to the k mod n, which implies we could raise both sides to the j power. So r to the j is congruent to m to the k to the j mod n, right? And this implies that r to the j is congruent to m to the kj mod n. Okay. Wonderful. Next, we're going to take a closer look at kj. Kj is congruent to 1 mod phi of n. We know this implies that kj minus 1 is congruent to 0 mod phi of n, which implies that kj minus 1 is equal to phi of n. Am I switching phi? We're past this. Times L for some L in the positive integers. Okay. So this implies that kj is equal to phi of n times L plus 1. Okay. And as r to the j is congruent to, it's right here. I'm not going to rewrite it. As we have this, we see that r to the j is congruent to m times the phi, right? We can just plug in phi of n times L plus 1 mod n, which is congruent to m times phi of n times L times m mod n. Okay. And now we're going to have to do a little bit of we have a couple of cases to prove why this works. We can erase this. Okay. I may want to hold on a bit. Okay. So our first case here is if the GCD of m and n is equal to 1, then m to the phi of n is congruent to 1 mod n. Okay, and Euler, his theorem tells us that r to the j is congruent to m to the phi of n times L times m, which is congruent to 1 times the L, 1 to the L, times m, which is congruent to m mod n. So we're done. The second case that we have to cover is if the GCD of m and n is not 1. Okay, as n is just the product of 2 primes p and q, we have subcases, a case of a case, if you will. So the first case of case 2 is that the GCD of m and n is in fact just pq. Another case is that the GCD of m and n is just p. And then lastly, the GCD of m and n is just q. These will have the same argument, as they're both primes. Okay. All right. So to prove 1 here, we have if the GCD of M and N is equal to P times Q, then we can say that M is equal to, we just know that N divides M, right? Because N is just P and Q. So immediately we get that M is congruent to 0 mod N. So we can say that M to the Kj is congruent to 0 to the Kj, which is congruent to 0, which is congruent to M mod N, right? And we know that R to the J is congruent to this piece. So we're done. And for 2 and 3, we have if the GCD of M and N is just one of the primes. I'm just going to go with Q here. Is Q, then M is equal to QS for some, S and Z, positive integer. We know that the GCD of S and P is equal to 1, and the GCD of S and N is equal to 1 as well. So, do some work down here. We have that R to the J is congruent to M to the K to the J. Sorry, that's true though. R to the J is congruent to M raised to K times J mod P. We have that M is equal to QS. We're going to make a substitution. So QS raised to the KJ mod P. We're still okay. We know what KJ is, right? KJ is just 5N times L plus 1. So we can make another substitution. QS times 5N times L plus 1 mod P. Right? And we know since phi of n here is just the product of 2 primes, we can plug in here that phi of n is just p minus 1 times q minus 1 times L, and then we can bring this down to just be QS mod P. And by Fermat's little theorem, the FLT, we see that as P does not divide QS, that QS raised to the P power is congruent to 1 mod P. I think it's P minus 1. Yeah, okay. So we have this. Oh, yeah, because then this will be 1. Okay, so we're back down to here. So we get to that this terrible notation is congruent to 1. Is congruent to 1 to the Q minus 1 times L, which is congruent to 1 mod P, which is just QS congruent to M mod P. Okay. And then, this is the last page. So, we're doing some damage on this QED count, by the way. We'll have 5, 10, 15, 20, 25, 30, 31. Is that prime? Maybe? Okay. We have R to the J is congruent to M to the K to the J times mod Q, which is congruent to 0 mod Q, as Q divides M, which is congruent to M mod Q, as M is congruent to 0 mod Q. So we see that R to the J is congruent to M mod Q. Therefore, R to the J is congruent to M times mod, congruent to M mod PQ. Okay, and the reason that this is true is another theorem that I'm not going to prove, but R to the J is congruent to M mod the LCM, lowest common multiple of P and Q, if R to the J is equal to m mod q and mod p. QD. Woo! All right, we're done. So this this is good. This is protecting like banking information. So good thing it took this long. All right. Okay, I think we can. Yeah.
Had to work for that.
Oh yeah, that was a doozy. Is 31 prime? Can someone Google that?
Pat says applause for you.
Wow, I'm so glad we got to 31 then. More than double. All right, who's next? Are we?
Next on the schedule is an appearance from a super secret special guest.
Ah, nice. Okay. Are we paused on the stream?
We are not. Do you want me to pause?
Yeah, we should.
Okay.
Okay. And hopefully we have some. This will eat up some time. Okay. Sorry, I forgot to do my conjecture. So first, we're going to find. We had talked about this a little bit earlier. The primordial numbers, Pn, is the product of the first n primes. So the Euclid numbers, this is, so Pn is the product of the first n prime. So like P1 is just 2, P2 is 2 times 3, P3 is 2 times 3 times 5. So we're going to take that and talk about what a Euclid number is. A Euclid number is just an integer that takes the form en equal to pn plus 1. So this is the number. So the first Euclid number, E1, is just 2 plus 1. E2 is 2 times 3 plus 1, which is 7. And I'm going to jump to E6 because I think that's fun. So we have 2 times 2 is equal to 2 times 3 times 5 times 7 times 11 times 13 plus 1. And this is equal to 30,031. Okay, and the reason I chose E6 is that this is the first non-prime Euclid number. So yeah, we could go to the next slide there. So the conjectures that have not been proved about these numbers is that there are an infinite number of prime Euclid numbers. You could probably just use that twin primes theorem on that one. Yeah. And then the other conjecture is that every Euclid number is square free. So yeah, that's the end of that. That's my conjecture. Or not my conjecture, just the conjecture for my portion. Okay, now we're done.
Thank you, Hanna.
Yes. Okay. See, that was my plan because now you guys have to play. Okay. All right.
10-minute break.
Okay.